For decades, physicists have relied on the lambda cold dark matter model to explain the universe. At the core of that model sits Albert Einstein's cosmological constant, or lambda. It describes dark energy as a steady, unchanging outward force that pushes the cosmos apart at a perfectly consistent rate. But observational data is tearing a hole in that assumption. When astronomers measure the expansion rate of the early universe using background radiation, they get a relatively slow speed. When they measure the local, modern universe using nearby stars, they find it expanding much faster. This gap between the two measurements is called the Hubble tension. The difference might seem small, a handful of kilometers per second per megaparsec, but it is too large to be a statistical fluke. Independent studies from around the world using entirely different distance measuring techniques have confirmed the gap over and over again. Two accurate measurements of the same universe are yielding incompatible answers. The Hubble tension exposes a mathematical fracture deep in our foundational model of reality. To find out exactly where the math breaks down, we need to map the cosmos with a completely new level of precision. Enter the Dark Energy Spectroscopic Instrument, or DESI. Mounted on a telescope in Arizona, DESI utilizes an intricate grid of 5,000 robotic fibers. Every 15 minutes, these tiny robots reposition themselves to capture light from distant galaxies, building a three-dimensional map spanning 11 billion years of cosmic history. This visualization shows baryon acoustic oscillations. These spherical bubbles act as a standard ruler. Physicists know their exact expected size to track cosmic expansion. But the white measurement bar connecting these bubbles reveals DESI's anomaly. The physical distance is tangibly smaller than standard equations predict. Clearly, the standard ruler doesn't fit the math. The data points to a bizarre conclusion. Dark energy is weakening. It exerted a stronger outward push in the ancient universe, and that acceleration is actively dropping off today. The cosmological constant is failing its most precise test. This statistical breaking point suggests that dark energy is a dynamic, evolving sector of the universe that the standard model simply cannot explain. To explain why dark energy is losing its grip, physicist Darrell Hargett proposed a framework called terminal tension cosmology. This theory treats spacetime as a physical material with an effective elastic modulus. Geometric strain carries a literal energy cost, meaning that as the universe stretches, it generates a back reaction that resists further expansion. As dark energy forces the universe to expand, the geometric strain builds up. Eventually, that tension begins to actively push back, opposing the outward force and acting as a brake on the universe's acceleration. Hargett defines this as the terminal tension regime. It is the absolute threshold where the geometry of space becomes so heavily strained that additional stretching is physically resisted. Confirming this hypothetical limit requires looking where space-time is already under the most extreme stress. We have to shift our scale drastically inward, toward the event horizon of a black hole. These massive collapsed stars serve as the ultimate localized testing ground for extreme gravitational strain. Classical physics assumes that the gravitational collapse inside a black hole continues forever, crushing matter down into a mathematically impossible, infinitely dense speck known as a singularity. Terminal tension cosmology rejects the singularity entirely. Instead, as the localized spacetime compresses, it hits its terminal tension threshold. The fabric reaches its maximum strain capacity before infinite collapse can actually occur. The collapse halts. The matter inside transitions into a stabilized, ultra-dense phase that remains safely contained entirely within the boundary of the event horizon. Black holes represent the ultimate demonstration of this saturation mechanism, arresting collapse before it destroys the geometry of space. If space-time can arrest an infinite collapse on a microscale, it can arrest infinite expansion on a macroscale. The exact same elastic limit stabilizing the core of a black hole is currently what is choking off the dark energy driving our universe apart. This unified mechanic rules out the most violent apocalyptic scenarios. The cosmos will not end in a big rip of infinite tearing, nor will it snap back into a sudden big crunch. Instead, the universe will stretch until it hits its maximum structural capacity, eventually settling into a permanent high-tension equilibrium. This schematic, showing the cross-section of the DESI instrument, highlights the massive machinery currently gathering the data to verify this. Over the next few years, DESI's continued mapping will definitively trace how dark energy is evolving over time. Simultaneously, instruments trained on black holes, like the Event Horizon Telescope, will scan the perimeters of collapsed stars, searching for microsignatures of this exact same tension limit. The weakening expansion and the observed stability of black holes reveal a universe actively pushing back against its own expansion, proving that even infinite reality has its limits.